So today we're going to start with half-life, which I'm sure you've heard about a lot and know how to do these calculations without much problem. But of course, we're just relating this to radioactivity. And so of course, that is the time that it takes for half of a radioactive sample to decay. And every radioactive substance has its own characteristic half-life. So here is your equation, which again, I'm 100% sure that you have seen before, probably in your math classes. But N is the radioactive nuclei remaining, and N naught is the original amount of radioactive nuclei. Multiply that by 1/2 to the power of N, and N is just the number of half-lives that have happened. So if you do need to then take that further into what is a half-life or how much time has passed, and to get the number of half-lives is just the total time divided by the half-life. Okay? So we're just going to go over how to use this equation, which I'm sure you already know how to do. But a few notes really quickly. N and naught, they can be measured in a bunch of different terms as long as they're in the same unit. So it can be measured in terms of mass. You can have kilograms or some of both things, or grams of both things. You can have a percentage of how much is left, which obviously in that case the original percentage is 100. You can use something called the number of nuclei that is present, or we can do something called the activity, which is measured in something called becquerels, which is how many decays per second. So that is just the number of nuclei that change in a given time period. So I know that's new for you, but again, you don't need to know much about it other than if N and N naught are both in becquerels, you are good, okay? So those two units just need to match. So whether they're any of these four different things, it doesn't really matter as long as they're in the same units, okay? And of course, we know that this is what a half-life graph looks like because it is a fraction to an exponent, or a number that's in between 0 and 1 to an exponent. It's something that exponentially decays like this. And of course, we know that, every half-life that it has, then the graph gets exponentially smaller. And that's what that's gonna look like. Okay, so let's do some calculation with this equation, which again, I'm quite sure you've seen before, had to deal with before. But let's go for it. So we have carbon-14 having a half-life of 5,730 years. What percentage of a sample of carbon-14 will remain after 1.719 times 10 to the 4 years? So when you hear about something called carbon dating, it's using carbon-14. And this is exactly why, because it has such a long half-life. So this is why we use carbon dating to date things, because again, if we can assume how much was present in the original and how much is there now, it really helps us figure out how old it is. So, I want to know how much is there after 1.719 years. So we have N is equal to N naught equaling, or times 1/2 to the power of N. Of course, N being the total number of years we have, or the total time we have, divided by the half-life, okay? Because again, N is how many half-lives have happened. So that's what N is going to be in the situation. So we just want what percentage, so we're going to assume that we start with 100% and want to see how much it goes down from there. So N naught can just be 100 here. Okay, so we just have 100 times 1/2 to the power of 1.719 times 10 to the 4 divided by 5,730. Okay, we put that into your calculator, you should get 12.5%. Okay. And there we go. That is what carbon dating is. It's using carbon-14 and seeing how much is left because it does have such a long half-life. So that, I'm sure you already know how to do. That one's nice and easy, where you just plug it into the equation and there's no rearranging. So I want to go over a different situation that you might need a bit more of a refresher with because we need to use logarithms. So if I have a 208 gram sample of sodium 24 and it decays to 13 grams within 60 hours, I want to know what's that half-life, okay? So I have my initial amount, which is n naught. We have what's happening after a certain amount of time, and we have how much time is happening total. So that's the total amount of time is 60 hours. So I need to figure out what the half-life is. So how do we do this? So again, n is the number of half-lives, so we need to figure out what this exponent is. When we're trying to figure out what an exponent is, we need to do what? We need to use logarithms. So what I'm first going to do is subtract or divide both sides by n naught, okay, and I get this. So now, of course, I'm going to take the logarithm of both sides so I can get rid of the n as an exponent, because there is a special logarithm law that I'll remind you of, but hopefully you already remember. All right, and that states if you're taking the log of 1/2 to the power of n, that is the same as, do you guys remember? N times the log of 1/2. So therefore, that gets that n out of the exponent for us, which is really good because how do you solve for it when it's in the exponent? Doesn't really make a lot of sense to me. Okay, so what do we get? We get n equaling the log of n over n naught, which if we put in the things here, n is 13 grams and naught was 208. And then we're going to divide that by the log of 1/2. Okay. And if you calculate that, that gets you 4. So that means that 4 half-lives have happened. So if I want to know what the half-life is, so remember that n is equal to the total time divided by the half-life, right? So if I want to know what the half-life is, then it's just total time divided by n. Okay, so our half-life should be, well, remember 60 hours passed. And our n we found out was 4, so therefore our half-life is, that's a loopy L, it just didn't work out. Our half-life is 15. And I guess I should put 15.0 hours. Okay, so that's just a little refresher for you from some Math 30. If you do need to solve for n ever, then we just need to use our logarithms. And it's basically, you're always going to get to this point, okay? It's just going to be these two numbers that are going to change, okay? So if you have any more questions about that, just email me, but I just went over it really quickly because I'm assuming all of you have pretty much learned this before. Okay, so that's that, and that's how we calculate the half-lives of radioactive substances.